In this video, we're going to calculate a volume of revolution where the axis is displaced again away from the x or the y axes. Here we're going to define the axis as x equals 6. And we're going to spin around that axis. We're going to take a region bounded by y equals square root of x, and y equals 0, and x equals 4. What that's going to lead us to is a natural way to slice this up as being horizontal. All the slices being delta y thick when we do that. That will give us a shape when we do these slices of rings. So we're going to have the... Go back a few seconds. With that construction and imagining these being spun around, we're going to see a hole in the middle and this structure here rotated around. That is going to give us rings in our slices. So the volume of a slice is going to equal the area of a ring times the thickness. The thickness we already know is going to be a small element of y. What we're going to need for the ring area, though, is an outer radius and an inner radius, where we take the area of the outer circle generated by spinning this all the way around, and we subtract the area of the inner circle, which is the hole, and that's pi r, the inner radius squared. Thickness, again, is just delta y. The way to be successful with these kinds of problems is to, again, have a very carefully labeled diagram. This distance here is between x equals 4 and x equals 6. That's much better known as 2. And we see, in fact, that every inner radius, the hole that we're building here, always has that same fixed radius of 2. So we know our r in already. The outer radius is a little trickier. We'll draw it in here. If we look for the outer radius, it's defined by a point on the graph y equals root x. Let's do a little sideline here. The outer radius is equal to something to do with the x-coordinate. But here we have a slightly different diagram than we've seen before. What we have is an entire distance here of 6. This distance here from the axis out to this point is the x-coordinate, but our radius is what is left over. Again, we've seen these kinds of constructions and optimization problems, related rates. You just have to be aware of it and keep an eye open for it in these diagrams. X is the distance from the axis to a point. This whole distance is 6. Our outer radius is 6 minus x. It's what's left over out of that 6. We're almost done. However, we need that expression in terms of y. So let's remember that this is the x value on the graph of y equals root x, or on the graph of x equals y squared. So 6 minus y squared is our outer radius. Can we verify that? Absolutely. When y is 0, when we take a slice of this height, we should have the radius from here all the way out to the origin. Oh, that's exactly 6 minus 0. When we get to the peak here, when y is 2, we should have an outer radius of 2 as well. 6 minus 2 squared, 6 minus 4 is in fact 2. We could check some other values as well, but this is a formula for the outer radius from the axis, which is over here of rotation, to the boundary defined by y equals root x. Again, the best advice, draw the diagrams and just be explicit about where your radius is. It's this distance here for the outer radius. How can we build that from the ingredients in the problem? Well, let's sub that in. We have pi, outer radius, 6 minus y squared. The radius then is squared, so we have another squared, minus pi times the inner radius, and that was always 2, and times the thickness, delta y. That is the volume of a slice. On the next page, we'll turn that into an integral and actually evaluate the integral. Here we've expressed our same slice volume, going back a page. 6 minus y squared all squared, and 2 squared. The only thing we need to add to make the integral work is the starting value for y. Well, it starts at y equals 0. The final slice is at y equals 2. So we're good to go there. Before we can evaluate this, we really should tidy it up though. It'll make it much easier to work with. We're going to have a common pi that we can bring out front. And then we might as well expand this because we can't really deal well with nested expressions in integrals. So this will be 36 minus 12y squared plus a y to the fourth and minus 4 pi. So the pi's out front, so it's just minus 4. Close that off. All of that is times our little increment of y. Before we do anything else, we can combine the 36 and the 4. So we'll have the integral from 0 to 2 of 32 minus 12y squared plus y to the fourth dy. We can now integrate, so this is just tidying. We have simple powers of y now that we can use our standard rules on. We'll have 32y's minus 12y cubed over 3 plus y to the 5 over 5. All of that evaluated between y equals 2 and y equals 0. That turns into pi times 32 times 2, 64. 12 times, actually that's just 4. So it'll be 4 times 2 cubed is 8. And that's times, and plus 32 over 5. Subbing in the 0 values, we get 0 minus 0 plus 0, that's just 0. And if we work that out, it gives us roughly 120.6 cubic units. Notice again, the integral process here fairly straightforward. Almost all the intellectual effort in this process was in building the volume of a slice formula. From this diagram, looking carefully at the distances, recognizing when coordinates were in there, that they were distances from axes, but we didn't want those in our calculations. That led us to this fairly simple function, but with a lot of work going in behind the scenes to get there. That led us to find the integral that defined the total volume of this solid of revolution.